All right. Hi, everyone. Welcome to another lecture in the Mathematical Methods course. All right. Today, we're going to be talking about something that maybe you know already, maybe you don't. It's continuous random variables. Okay. So, we've already talked about something similar called the discrete random variables. All right. And we learned that they are something that have a finite number of values. Okay. So, like flipping coins or rolling a dice. Okay. Finite number of outcomes is a discrete random variable, and infinite number of outcomes is a continuous random variable. We've already talked about some of the differences beforehand, so today we are going to focus on a little bit more advanced slash technical stuff. All right. So first of all, there are infinite number of outcomes. Okay. Secondly, because there is an infinite number of outcomes, you can never give a precise value. Like, for example, I'll tell it with the example, right? For example, you are measuring the height of someone as a continuous random variable, right? Now, if you start measuring it, okay, if you start measuring it and you go, it's 5 feet, then you can try and be a bit more precise and you can say it's 5 feet and 1 inches. Then you can be a bit more precise and you can be 5 feet, 1.5 inches. And you can just keep doing that and you can keep getting more and more precise infinitely, all right? So you can see that it can gain an infinite precision, all right? Which is why there's an infinite number of outcomes in the first place, because if you're trying to measure the height between, 5 and 6 feet, there's an infinite number of values in there. There's an infinite number of outcomes in there. That's how the two are related, okay? So typically, continuous random variables take up decimal values, okay? That's one of the, another one of the things about them, another one of the observation about continuous random variables, okay? So, moving on, because of this infinite precision, you can never say somebody is 5 feet, 2 inches, and 50 centimeter tall. Okay, you can never do that. You can only say that the height of someone is between 5 feet and 6 feet. Well, not that big, but you can always just give it a range. You cannot be exact with continuous random variables because, like I said, you can always be more precise. So what do? You just give it a range. So it's either between 5 foot 1 inches or 5 foot 2 inches. Okay? So it's stuff like that. And again, it can be any value inside that range. Great. Moving on. So we've looked at discrete random variables. We've looked at ways to visualize it. Okay? We had stuff like probability tables and stuff like that. Okay? So what do we do here? How do we describe it? We use another table, okay, which is called a frequency table. Now, knowing how this works is not as important as the probability distribution table from discrete random variables, but it's still good to know how it works. Okay, so frequency table. On the left-hand side, we have ranges. Right-hand side, obviously, frequencies. Okay, so how does this look? Again, coming back to our example of measuring heights, we can say that the ranges are in feet, okay? We can say one range is 5 to 5.5. Another range is 5 to 6. And you measure 10 people and you say 6 of them were between 5 and 5 foot and 5.5 feet, okay? And 4 of them were between 5.5 and 6 feet, okay? That is what a frequency table looks like, all right? Now what you do with it is you can plot out a histogram, okay? So looking at a histogram. Okay, so this is the more important part. Okay, frequency table, not as important. This one, very important. Need to pay attention. Okay, so you go 1, 2, 3, 4, 5. Should have thought more about my axes, but that's okay. 5, 5.5, and 6. Okay, they're not. That's not how you're supposed to draw it. The axes should be consistent, but for our purposes, it's fine. All right, and now we have a frequency of 4, 5, and 6. Okay, so as you can see, between 5 and 5.5, there's 6 people. So what we do is we take that to our range. So our range is currently 5 to 5.5. and we just create a sort of a rectangle, a bar, and you shade that in. And similarly, 5.5 to 6, 4 feet, or 4 people, sorry, and there is your second bar. And that is a histogram, okay? And that's typically how you describe a continuous random variables, okay? So now that is your basics cleared. Now you know everything about continuous random variables at a fundamental level, okay? What we're going to look at now is something a lot more cooler, okay? Something that relates to calculus, actually. So if you see here, our ranges are pretty big, all right? Once you start to sort of narrow the ranges down, your histogram starts to become sort of like this, all right? And if you keep narrowing it and narrowing it and narrowing it, it starts to become like this, okay? If you keep doing that and you just look at the top of the things, it'll start looking like a curve, all right? So narrowing the ranges, narrowing them further, and then narrowing them, keep narrowing them, you'll see that it starts to look like a line, all right? And this line, once it becomes a line, we call it a probability density function, okay? Very important thing, a probability density function, all right? So, using this probability density function, you can then find out things about the continuous random variable itself, okay? There we go. So, that is one more thing about continuous random variables. Now, how does that come into calculus? Good question. There's a function, there's a curve, so obviously you can start thinking about calculus already. But the important part is, for example, if this was 5 and this was 6, and I want to find out the probability that someone is between 5 feet and 5.2 feet. Okay, so I want to know the probability that someone is in this range here. Okay, you know what that probability is? It's the area under that curve for that range. Okay, that is the probability of being between 5 to 5.2 or any values in that given range. That is the best part about it. Okay, so I'll just write that down in a different color so it stands out. So the probability of being between A and B for a given function, probability distribution function, the probability is equal to the integral, so the area under the curve, from A to B of the probability distribution function. Okay? Very important thing. And that is going to basically change everything from this point onwards. Also, if you note something very important, there's an A and there's a B. So if the A and the B are the same, so for example, if I want to know the probability that someone is exactly 5.2 feet, okay, not a range, what will happen here? It will be 5.2, 5.2. When you integrate that, you get 0, okay? So if you do try and do that, you get that the probability is 0, which is true. You can never get an exact value with continuous random variables, okay? And that is almost everything. Just one more thing is that if you have a range from 1 to 5, okay, that's your entire range where the values can come in, then if you remember for discrete random variables, the total probability of everything is equal to 1. Similarly here, the area under the entire curve area under entire curve is equal to 1, okay? That is another important part about probability distribution functions. And similar to before, no probabilities can be, so the probabilities have to be between 0 and 1, okay? So instead I'll write it like this. probabilities, I can't spell, are always between 0 and 1. Therefore, the probability distribution function that you're looking at for the given range has to be between 0 and 1. It can never go above that. It can never go below the x-axis. And with that, we have completed everything that you need to know about continuous random variables, apart from the mean and the mode. But we'll get to that. That is more simple. This was an important lecture, okay, to grasp what is really happening, and it's going to set a good fun foundation for your later tests, okay? So, to wrap off, let's do some questions, okay, really quickly, and we'll get them over and we'll move on. Okay, so the first thing is, this is straight from the workbook, by the way. We have a probability distribution function. F of x is equal to 2x over 3, take 2x squared over 9, okay? And x is between 0 and 3. See? When you have a probability distribution function, you always have a range, okay? Either you'll be given that or you'll have to figure it out yourself using these two thingies, these two rules for probability distribution functions, okay? Using those two, you have to figure out the range. But the range is always going to be there, okay? So, now what do we do? Part A asks you to sketch the graph, okay? Obviously, we are very capable of that. We've been doing that pretty much our whole lives at this point. We can sketch a graph. It's a quadratic, okay? I have the solution in front of me, so I'll just copy that off. Like I said, it's a quadratic facing downwards, okay? And that is your f of x. Cool. All right. Remembering you're putting your x's labels. Okay, very nice. Now what do we do? It asks us to find if f of x is valid, if it is a valid distribution function, okay? How do we check that? Obviously, we come back to our rules, right? So the area under the curve has to be 1, and the probabilities always have to be between 0 and 1. So first thing first, which one should we go with first? I think just finding if it's less than or greater than 1 at any point is the easiest point, or easiest one to go with, okay? So first of all, you can see that all values are above 0. Tick. Second of all, they need to be less than 1, all right? So we need to know if the graph goes above 1. How can we do that? Well, we can look at this point, right, can't we? This is an easy point to find, all right? And we could just say, if this point is above 1, then we have a single point that is above 1, and that completely ruins it, all right? Even if there's a single point. So, okay, just look at this, and if it's above 1, oh no, if it is less than 1, then the max value is less than 1, therefore the whole function is less than 1. So we are good to go. So, we'll look at that now. Knowing quadratics, we don't have to do calculus, but sometimes you do, okay? Knowing your quadratics, you will know that the max occurs between the two zeros, so at 1.5, okay? In this case, the max value is something that you have to put into here, okay? So you go f of 1.5 to find the max value. That is 2 times 1.5 all over 3, okay? Take 2 times 1.5 squared all over 9, all right? So if you just quickly calculate that, that becomes 1 over 2, that's just 1. I think that makes sense. Oh no, that makes sense, all right. Very nice. And 2 times 1.5 times 1.5. Okay, well, I can just do the same thing I did before. I'm doing this without a calculator, that's why it seems like a bit of a struggle, but that is okay. All right, there you go. And now if I put that together, this becomes a 1 over 2, giving me a 1 over 2. So we are saying that the maximum value is 1 over 2. Therefore, the whole function is below 1. Great stuff, all right? So first requirement, that the probabilities are always between 0 and 1, has been checked. Now let's look at the second requirement, that the total probabilities are equal to 1. How do we do that? Get the area under the entire curve, or the specified range. All right, so we go finding the area, or the probability. We go integral from 0 to 3 of f of x dx. Okay, so let's put that through, what was that again? 2x over 3, take 2x squared over 9 dx. All right, let's hope I don't make a mistake here. You get 2 on 6x squared, I believe. Yep, that seems about right. Okay, and then you get 2 on 27x cubed. Let me go from there to there. All right, very nice. Okay, so hopefully you've been having practice with your integration. So if I skip a few steps, it should not be an issue. Okay, and when you try and solve that out, you get that this cancels out, and you have sorry, oopsies, I should have showed that a bit better. You get that this becomes like that cancels out with this, and you get 3j2 equals 1. Okay, a lot of cancelling out and a lot of this and that, but at the end we get 1. Okay, which means that the total probability, the total area under the curve, is 1. Second requirement has also been satisfied. Very cool. And now it asks us to find the probability that a value is between 0 and 1. Okay, like we've said, find the integral from 0 to 1. Simple stuff, all right? In fact, already now, we have the antiderivative. We can just sub it in here, okay? We don't have to calculate it again. Take 2 over 27 x cubed. Sorry about that. And when you plug that in, you get 2 over 6, take 2 over 27. And whatever you get from that, that is your final probability. Okay? So, as you can see, very straightforward process. Okay? Once you find out your probability distribution function, it's really easy. Okay? It's just some calculation, just some integration, and you'll be fine. And you know what the best part is? You can do all of this on your calculator. So you can almost never go wrong with this. Okay? So yeah, that is all for this lecture. Next lecture, we are going to look at some means, modes, medians, stuff like that. So yeah, we'll see you there.